Welcome everyone to the Spectral Geometry and the Cloud seminar. Today we have Panagiotis Polymerakis from University of Thessaly, and he will speak about large Steklov eigenvalues under geometric constraints. The stage is yours, Panagiotis.
Thank you very much. So today we'll discuss about a couple of constructions producing large Steklov eigenvalues under certain geometric constraints. So throughout this talk, manifolds will always be assumed to be connected, almost always compact actually, with possibly non-connected and smooth boundary. So let them be a compact Riemannian manifold with boundary. Will always denote by me the outward pointing unit normal. The boundary. The Steklov spectrum of M consists of all real numbers sigma, such that there exists a non-zero harmonic function, with normal derivative being sigma times itself. Boundary. Elements of the Steklov spectrum are called Steklov eigenvalues and form an increasing sequence, which will denote by sigma 0, sigma 1, sigma 2, and so on, where sigma 0 is always 0, since constant functions are Steklov eigenvalues corresponding to 0, and sigma 1 is positive, since we assume that our manifold is connected. Now, the interplay between Steklov eigenvalues and the geometry of the manifold has been extensively studied during the last years. And in this talk, we'll give a couple of constructions which are joint work with Alexandre Girouard related to producing large Steklov eigenvalues, and in particular, in the first part of the talk, on certain Riemannian manifolds, we'll construct the Riemannian metrics which are prescribed on the boundary, have fixed volume and arbitrary large first non-zero Steklov value. And in the second part of the talk, we'll construct submanifolds of the Euclidean space with prescribed boundary and arbitrary large first non-zero Steklov value. So to put our constructions into perspective, let's recall that if we have a compact surface with boundary, then the first normalized Steklov eigenvalue, that is the first Steklov eigenvalue times the length of the boundary, is bound from above in terms of topological invariance. Surface, something which is quite atypical. In higher dimensions, there is nothing analogous, and more precisely, it is known that if we have a compact Riemannian manifold of dimension at least 3, then there exist conformal Riemannian metrics, which coincide with the original metric on the boundary, have arbitrarily large first non-zero Steklov eigenvalue. It is also known that with respect to these metrics, the volumes are also unbounded. And this gave rise to the following question. If we have a Riemannian manifold, can we find a sequence of Riemannian metrics which coincide on the boundary, have fixed volume and arbitrary large first non-zero Steklov eigenvalue? Certainly, this is not the case for surfaces. For higher dimensions, there have been a construction by Janssen and Girouard, namely for manifolds of dimension at least 4. The method is based on adapting an old method about closed Riemannian manifolds involving the first non-zero Laplace eigenvalue. And so they adapt this method on the boundary of the manifold in question. So the boundary has to be of dimension at least 3, thus the whole manifold of dimension at least 4. So this question is widely open for 3-dimensional manifolds. In the first part of the talk, we'll give examples of such Riemannian metrics on 3 dimensions, on certain type 3-dimensional Riemannian manifolds, but also on manifolds of higher dimension, which are different from the one arising from this construction. More precisely, the main result of the third part of the talk is the following. Suppose that we have the Riemannian product of a compact manifold with boundary with a closed lower dimensional Riemannian manifold. For instance, a surface with boundary times a circle. Then we can find on it a sequence of Riemannian metrics which coincide near the boundary actually with the product metric, have the same volume element, not just the same volume, and have arbitrarily large first non-zero Steklov eigenvalue. It's worth to point out that our assumption on the dimension of the factors is very important. For instance, if both factors are one-dimensional, so we have an interval times a circle, then the product is a cylinder, and of course the assertion does not hold in this case. Our approach for this problem is drawing heavily from the aforementioned work on conformal Riemannian metrics. However, the novelty of our method is that we study work products, express the Steklov spectrum of a work product in terms of Laplace type operators on the base manifold, and then work with Laplace type operators similarly to the work that has been done on conformal Riemannian metrics. So let's begin by briefly recalling a few things on Laplace type operators. So let M be a compact Riemannian manifold boundary denoted by an eta pointing normal to the boundary. A diffusion operator on M is an operator of the form Laplacian minus gradient of Ln of a positive smooth function H. And by this we mean that given a smooth function f, L on f is the Laplacian of f minus the inner product of this vector field with the gradient of f. Or generally, a symmetric Laplace type operator on our manifold is just a diffusion operator plus a smooth function which we call potential Laplace type operator. And it's quite customary to consider such operators on Riemannian manifolds in weighted L2 spaces rather than L2 spaces themselves. More precisely, if we have such a Laplace type operator, we consider it in the weighted L2 space L2 with index h of M, which is just the L2 space with this inner product. And it turns out that this operator, defined on the space of smooth functions which vanish on the boundary of our manifold in this weighted L2 space, is symmetric and actually essentially self-adjoint. That is, it has a unique self-adjoint extension, and the spectrum of this self-adjoint extension is discrete and actually consists of all real numbers lambda, such that there exists a non-zero smooth function f with sf being lambda f, the manifold, which vanishes on the boundary. And it follows from Rayleigh's theorem that the smallest element in the spectrum of this operator is the minimum of Rayleigh quotients, that is, these expressions. And from this, we readily see that if the potential P is non-negative, then this quantity is positive, so zero is not in the spectrum of this self-adjoint operator, which means that this operator is actually bijective. And from this, it follows that any smooth function on the boundary of our manifold has a unique S-harmonic extension, that is, a smooth extension with S on this function being zero. And this allows us to define the modified Dirichlet-Neumann map as follows. Given a smooth function on the boundary, say f, we get the normal derivative of the S-harmonic extension of f. And again, we consider this operator in the weighted L2 space boundary, and it turns out that this operator is symmetric and essentially self-adjoint with discrete spectrum, which we'll denote by sigma s, and consists of all real numbers sigma, such that there exists a non-zero S-harmonic function with normal derivative being sigma times itself on the boundary. Elements in the spectrum of this operator will be called Steklov eigenvalues of S and will be denoted by sigma 0 of S, sigma 1 of S, and so on, as in the case of the usual Steklov spectrum. And again, from Rayleigh's theorem, we are able to derive some expression for these eigenvalues. We readily see that the smallest eigenvalue of S is given by the minimum of Rayleigh quotients over all smooth functions in our manifold. So initially, from Rayleigh's theorem, we get that the smallest eigenvalue is the minimum of these quantities over all S-harmonic functions on the manifold. However, exactly as in the case of the Steklov spectrum, it turns out that given a smooth function on the boundary, the numerator is minimized by the S-harmonic extension of it. So here, taking the minimum over all smooth functions and overall S-harmonic function is actually the same thing. So we have this expression for the smallest eigenvalue, and we see that if the potential is positive, then the smallest eigenvalue is also positive. In the case where the potential is zero, that is, we have the diffusion operator L, then we have that the smallest Steklov eigenvalue is zero, since constant functions are L-harmonic with normal derivative zero. And again, we exploit Rayleigh's theorem to derive an expression for the first Steklov eigenvalue, first non-zero value, and that is the minimum of Rayleigh quotients over all smooth functions which are perpendicular to the constant function on this weighted L2 space. That is the integral on the boundary of f times h is equal to 0. And it's worth to point out that if this weight function h is 1 on the boundary, as it will be in our construction sequel, and the dimension of the manifold is at least 3, then actually the Steklov spectrum of a diffusion operator is just the Steklov spectrum of our manifold with respect to a conformal Riemannian metric. However, in dimension 2, for surfaces, this thing is something completely different. And let's close this preliminary section with a quite classic remark, which will play a quite important role in both parts of the talk. Let's recall the min-max characterization eigenvalues. So suppose that we have a compact Riemannian manifold M of dimension p, then the k plus 1 actually, Steklov eigenvalue of M is given as the minimum over all k plus 1 dimensional subspaces of the space of smooth functions of the maximum subspaces. And the interesting thing with this expression is that although our operator is defined in a quite more complicated way, in this expression we do not have any derivatives of the Riemannian metric. So we have two different Riemannian metrics of manifold, which are close only in the C0 sense. Then these quantities are uniformly comparable. So to be more precise, we say that two Riemannian metrics, G1 and G2, on our manifold are quasi-isometric with ratio C, if lengths are uniformly comparable. Okay? And this allows us to compare the norm of the gradient of functions with respect to these metrics and also volume elements. So from the min-max characterization, we obtain that in this case, Steklov eigenvalues are uniformly comparable with respect to this. Okay, now let's start our discussion on work products. So let N be a compact Riemannian manifold boundary and Fj a k-dimensional closed Riemannian manifold. Given a positive smooth function h on the manifold N, the work product is just the product manifold and not with this Riemannian metric. So work product with index h in our notation means that we have the factor h squared. Yeah. And in general, there are a few works illustrating that the Laplacian on the work product is more closely related to a diffusion operator on the base manifold rather than the Laplacian itself on the base manifold. More precisely, if we consider this diffusion operator on the base manifold, where the function is the working function to the dimension of the fiber, then we have the following. If we consider a smooth function of the base manifold N, and the corresponding function of the work product, then the Laplacian of the work product is equal to this operator on the function f on the base. And this pretty simple observation allows us to extend the quite well-known expression for the Steklov spectrum, the Riemannian product, to the setting of work products. More precisely, let's recall that if we have the Riemannian product of N with F, then the Steklov spectrum of it is given as the union with lambda in the Laplace spectrum of the fiber of this Steklov spectra on the base manifold. So for work products, using diffusion operators, we extend this quite naturally as follows. If we have the work product N with F, with working function H, we consider the diffusion operator we just mentioned. And then the Steklov spectrum of the work product is the union with lambda in the Laplace spectrum of the fiber of these Laplace type operators. And the proof for this is pretty simple and quite similar to the case of the Riemannian product. It's just by separation of varieties, essentially. So we consider on a normal basis Pi, say, of L2 of the fiber, consisting of eigenfunctions of the Laplacian. If we consider the corresponding functions in the work product, then we have this very nice formula for the Laplacian of them. And then for its I, we consider the corresponding Steklov eigenproblem on the base manifold n. And now if we consider the corresponding functions on the word product, we multiply them by phi, we get harmonic functions which also satisfy Steklov boundary conditions. So we have that each of these Steklov spectra are contained in the Steklov spectrum of the word product. And finally, it is easily checked that if we do this for all I, then we obtain an orthonormal basis of L2 boundary. Therefore, in this way, we have obtained the whole Steklov spectrum of the world. Okay, so the idea for the main result of the first part of the talk, as we mentioned, is based on word products. So we have this pretty nice expression for the Steklov spectrum of the word product. Now we want to consider such kind of operators, the Laplace type operator for lambda non-zero and the diffusion operator for lambda zero on the base manifold and examine whether we can make the first eigenvalue arbitrarily large. Okay, now for a part of this discussion, we'll actually suppose that in addition that the boundary of the base manifold n has a cylindrical neighborhood, that is a neighborhood isometric to the boundary times interval. However, this will not be restricted for our purposes. We'll just drop it at some point. And we begin with the first auxiliary proposition. So let M be a compact Riemannian manifold boundary of dimension at least 2, such that the boundary has a cylindrical neighborhood. And we fix a parameter delta between 0 and 1, which is totally irrelevant for this proposition, but is quite important sequel. Then, for any sufficiently small epsilon positive, we can find a smooth function h, which is 1 in a neighborhood boundary, is greater or equal to epsilon to the delta in the whole manifold, and the quality holds on a certain domain, such that the first non-zero Steklov eigenvalue, the corresponding diffusion operator, is arbitrarily large as epsilon goes to 0. In particular, this means that if n is a surface, for instance, then we can find diffusion operators such that the first normalized Steklov eigenvalue is arbitrarily large. So by studying these more made-up operators on surfaces, we're actually free from the topological restrictions that we have when we study the usual Steklov spectrum. And the proof for this proposition is actually almost identical to the result on conformal Riemannian metrics. So we won't really discuss this in detail. It's worth to point out that the assumption that the boundary has a cylindrical neighborhood is quite important for the estimates involved to establish this. Namely, in order to estimate the energy of an arbitrary test function, one uses its Fourier decomposition of the slices of the boundary in that cylindrical neighborhood. And from this, we're able, modulo some technical details, to establish our main result in the case where the boundary of the base manifold has a cylinder. Good. So let M be the product of a compact manifold N with boundary with a closed lower dimensional manifold F, and suppose that the boundary of N has a cylinder. Good. Then for any epsilon positive, there is a positive smooth function H on the base manifold N, which is 1 in the neighborhood of the boundary, such that with respect to this very specific Riemannian metric, the first eigenvalue of the product manifold is arbitrarily large as epsilon goes to 0. And this Riemannian metric is quite natural, namely, we consider the word product of N with F, and then we just rescale in the horizontal space so that the volume element of this metric is the same as the volume element of the product metric. And the idea to prove this is the following. Let H be a smooth function, which is positive and 1 on the boundary.
May I ask a question before?
Yes, sure.
So here, this condition that on a neighborhood of the boundary, it should be isometric to the product. So this is because earlier you mentioned that if it's if two metric are close to each other, then you can compare a Steklov eigenvalue. So it's almost product also is fine, right? You don't need the so if you know that it's very close to the product, then you can use the comparison. Am I right? Or
yes, I guess that one should be able to somehow modify it slightly. Actually, we'll be using this to drop this assumption in the sequel. But
okay.
yeah, probably there could be a slight modification. Yeah, also in the general setting.
Okay, thank you.
Okay, so we begin with such a function which will be specified theoretically, at least in the sequel. Then n, endowed with this metric of the statement, is actually the word product of the base manifold n, endowed with this conformal metric, with f, with working function h. So we already have an expression for the Steklov spectrum of this manifold. So we consider the corresponding diffusion operator on the base manifold, and we know that the Steklov spectrum of M is the union of the spectra of these diffusion operators, where lambda is in the spectrum of the fiber. So here we have 0 coming from the smallest eigenvalue of this operator for lambda being 0. So if we remove it and consider the minimum, that is the first non-zero Steklov eigenvalue of the word product, that is the minimum of the first non-zero Steklov eigenvalue of the diffusion operator, and the minimum of the smallest eigenvalue of the rest of the operators. However, from Rayleigh's theorem, the expression we already shown, we see that this quantity is non-decreasing with respect to lambda, so this minimum is achieved for the smallest possible lambda, that is the first non-zero Laplace eigenvalue of the fiber. So the smallest non-zero Steklov eigenvalue of the word product is the minimum of these two quantities. We express these quantities with respect to the original Riemannian metric of n, where we have the cylindrical neighborhood, so we can apply the previous proposition. And from the previous proposition, we know how to make the first quantity arbitrarily large. And it turns out that in order to make the second one also arbitrarily large, we need to choose the parameter delta from the previous proposition less than 1 and greater than the quotient of the dimensions of the factors. That's where that assumption comes in our proof. Okay, so very roughly speaking, this is the main idea on how to establish our main result under the additional assumption that the boundary of the base manifold has a cylindrical neighborhood. And now that we have this result, we're able to drop this assumption. So basically, we're in the exact same setting as the previous proposition, but now we don't have the assumption that the boundary of n has a cylindrical neighborhood. And to establish this in full generality, we just have to notice that the Riemannian metric of the base manifold is quasi-isometric to a Riemannian metric, say G prime, with respect to which the boundary has a cylindrical neighborhood. So we can apply the previous version of our result with this more convenient Riemannian metric of the base manifold. So we can find smooth functions Hn, which are one on the boundary and actually neighborhoods of the boundary, such that with respect to these Riemannian metrics on the product manifold, the first non-zero Steklov eigenvalues are very large. And then we can define the analogous Riemannian metrics where we use the original metric of the base manifold instead of the more convenient one. And it is easily checked that these two are quasi-isometric with the same ratio as the original metrics of n. So first Steklov eigenvalues are uniformly comparable. And that's how we obtain the result in full generality. And we actually have a variant of this result, which follows by extending everything we just mentioned to the setting of mixed Steklov-Neumann eigenvalues. And the variant is the following. So suppose that we have a compact Riemannian manifold with connected boundary, which splits as the Riemannian product of two manifolds. That is, we suppose just the boundary is a product, not the whole manifold. Then there is a sequence of Riemannian metrics, manifold which coincide on the boundary, have the same volume, not volume element, necessarily, and have arbitrarily large first non-zero Steklov value. And as we said, this follows quite easily by the extension of the previous result to this setting of mixed Steklov-Neumann spectrum. Okay, so first of all, in this setting, we may suppose that the boundary has a cylindrical neighborhood. So we begin with the Riemannian metric on the boundary. We extend it to the product metric in a sufficiently small neighborhood of the boundary, and then extend it to a Riemannian metric on the whole manifold so that it has the same volume. And in this step is actually that we lose control of the volume element. That's why we are able to say something only about the volume of the whole manifold. And now our assumption is that the boundary is the product of two manifolds, say F1 and F2, the dimension of F1 greater or equal to the dimension of F2. And then we set N, as in the previous result, to be F1 times the interval L, and then the cylindrical neighborhood of the boundary is actually the Riemannian product of N with F2, where the dimension of N is strictly greater than the dimension of F2. So we can apply the previous result, or more precisely its version for the mixed spectrum, and obtain that there exist Riemannian metrics in this neighborhood K, which coincide with the original metric in a neighborhood of the boundary of K, that is boundary of M times 0, that is the original boundary for manifold, and the boundary of M times L, that is then the cylindrical neighborhood in the manifold, with the same volume, and such that the first mixed Steklov-Neumann eigenvalue is arbitrarily large, where we impose Steklov in the real boundary for manifold and Neumann in this made-up boundary component. Now, since these metrics coincide with the original metric G in a neighborhood of boundary of M times L, the slice at the end of the cylindrical neighborhood, we can just extend them by the original metric of the whole manifold and obtain Riemannian metrics with the same volume, which of course coincide with the original metric on the boundary, and have an arbitrarily large first non-zero Steklov eigenvalue, since we have this for the mixed Steklov-Neumann. In this concludes the discussion for the first part. Now we pass to the second part related to submanifolds of the Euclidean space. And our construction is related to a result estimating eigenvalues of submanifolds of the Euclidean space. More precisely, if sigma is a closed submanifold of the Euclidean space, then there exists a constant dependent on sigma, such that for any compact submanifold of the Euclidean space with boundary sigma, we have such an estimate for its Steklov eigenvalues. And it is quite interesting what is the relation to the first part of the talk, these constructions of metrics which are prescribed on the boundary have fixed volume at sigma 1 arbitrarily large. So we have one of the examples that we discussed in the first part of the talk. So on a manifold MG, we have a sequence of Riemannian metrics Gn, which coincide on the boundary, have fixed volume, and sigma 1 arbitrarily large. So basically, we can think of these things as a sequence of Riemannian manifolds, M and dot with Gn. All of them can be embedded into some Euclidean space of sufficiently large dimension. So we obtain a sequence of submanifolds of the Euclidean space with isometric boundaries, fixed volume, and arbitrarily large sigma 1. So we see from this result that these constants, depending on the boundary, cannot be chosen the same. So this means actually that the boundaries of the submanifold are isometric, however, they're not congruent. That is, there is no isometry of the Euclidean space mapping one to the other. Okay, so there is this very elegant result about estimating Steklov eigenvalues of submanifolds of the Euclidean space. And as it was also pointed out in that paper, there is, strictly speaking, no example illustrating that the volume of M in this estimate is really needed, in the sense that there is no example of a sequence of submanifolds of the Euclidean space with fixed boundary and arbitrarily large first non-zero Steklov eigenvalue. So, in the second part of the talk, we'll construct such submanifolds, and actually we are able to construct such a sequence of submanifolds in any non-trivial case. More precisely, suppose that we have a compact submanifold of a Euclidean space with boundary of dimension at least 2 and codimension at least 1. So we are not interested in curves, we're not interested in domains of the Euclidean space. In any other case, in any tubular neighborhood of our submanifold, there is a sequence of compact submanifolds with the same boundary and arbitrarily large first non-zero Steklov eigenvalue. And in addition, if our submanifold is of dimension at least 3, then these submanifolds may be chosen to be diffeomorphic. And of course, in the case of surfaces, this is not possible since we have a sequence of surfaces with fixed boundary length and sigma 1 going to infinity, then the Euler characteristic of these surfaces must go to minus infinity, so they cannot be diffeomorphic. Okay, so due to this difference, we formulate this result in 2 parts. So for surfaces, it's formulated exactly as we just said. However, for higher dimension manifolds, we'll formulate it in terms of different embeddings of the same manifold. So more precisely, for higher dimensional submanifold, our result is the following. Let F from M to Euclidean space be an isometric embedding, a compact manifold with boundary, dimension at least 3 and codimension at least 1. Then there exists a sequence of embeddings, the same manifold into the same Euclidean space, which coincide with the original embedding in a neighborhood. Converge the original embedding uniformly, and the first eigenvalue of M endowed with a metric induced from the Euclidean space via Fn. So the first eigenvalue of the submanifold that we see in the Euclidean space is arbitrarily large. Our approach for this result is based on the C1 embedding theorem, which has already been exploited in the case of closed submanifolds of the Euclidean space. However, in our setting, we have to be quite more careful in applying it in order to obtain submanifolds with the same boundary. Okay, so let's recall the standard version of the C1 embedding theorem for manifolds. So let F be an embedding of a Riemannian manifold into Euclidean space. We say that F is isometric in a domain K manifold if it preserves the lengths of tangent vectors at points in. We say that the embedding is strictly short in a domain U of our manifold if it strictly decreases lengths of non-zero vectors tangent at points of the domain U. And the original version of the C1 embedding theorem by Nash and Kuiper, done by Nash for submanifolds of codimension at least 2, and extended by Kuiper to submanifolds of codimension 1, asserts the following. Suppose that F is a strictly short embedding of a closed Riemannian manifold into Euclidean space of larger dimension. Then, for any epsilon positive, there is a C1 isometric embedding from the manifold into the Euclidean space, which is C0 close to the original embedding. This illustrates that C1 isometric embeddings are much more flexible than more regular embeddings. For instance, there is the C1 isometric embedding from a sphere of arbitrarily large radius into a ball of arbitrarily small radius. And also there is isometric embeddings from any closed orientable hyperbolic surface into the three-dimensional Euclidean space. So basically, the restrictions that we know from basic differential geometry do not apply to C1 isometric embeddings, basically because we cannot define the Gaussian curvature of a C1 surface in the Euclidean space as we usually do in differential geometry. So the idea in order to prove this result is basically to distort the original embedding in order to spend all this extra length that we have with respect to the Riemannian metric outside the Euclidean space. And it's quite technical and difficult. However, recursively, this gives rise to a sequence of smooth embeddings, which is cosine C1. So it converges in C1, and the limit turns out to be isometric. Okay, so in principle, we may think of the C1 embedding theorem as an approximational result. If we have a short embedding, it can be approximated in C0 by C1 isometric embeddings. So in this sense, it's not a surprise that we have a relative version of this theorem, and namely the version that we're interested in is the following. Let F be an embedding of a compact Riemannian manifold boundary into Euclidean space of higher dimension, which is isometric in a neighborhood of the boundary and strictly short elsewhere. Then it can be approximated in C0 by C1 isometric embeddings, which coincide with the original embedding in a neighborhood of the boundary. Okay, so this is also a quite standard version among the experts, at least I guess, of the C1 embedding theorem, and will be quite important for our construction. However, we're not really interested in C1 embeddings and C1 submanifolds, since, as we said, it can behave very, very weirdly. So in order to obtain something interesting from this theorem, we need to approximate this C1 isometric embedding by smooth embeddings in the C1 sense. Okay, of course, in this case, our C1 isometric embedding coincides with the original embedding in a neighborhood of the boundary, so it is already smooth in a neighborhood of the boundary. So we can approximate it by smooth maps which coincide with the original embedding in a neighborhood of the boundary. And these maps will be C0 close, this C1 isometric embedding, which is already C0 close to the original embedding. So in this case, the exact same setting, we can find smooth embeddings which coincide with the original embedding in a neighborhood of the boundary, are C0 close to the original embedding. However, we have C1 convergence of smooth embeddings to this C1 isometric embedding. So the induced metric from these embeddings is C0 close to the original Riemannian metric of M. Okay, so in particular, Steklov eigenvalues are uniformly comparable. So with this approximation, we get that the first eigenvalue of the submanifolds that we see in space is actually comparable to the first Steklov eigenvalue of M dot with its Riemannian metric outside the Euclidean space. Okay, so basically, if we are somehow able to apply this corollary, we are able to find submanifolds, the Euclidean space, namely this F epsilon of M, are submanifolds of the Euclidean space, which are have the same boundary as the original submanifold, are close to the original submanifold. However, the first step of eigenvalue is comparable to what happens outside the Euclidean space. And basically, this is the central tool for the constructions of this second part of the talk. Given a submanifold of the Euclidean space, we actually think of it outside the Euclidean space. There we are able to change its Riemannian metric quite more flexible, we would be able to do inside the Euclidean space. And if we are able to apply this corollary, then we're done. Okay, so from this, the result on higher dimensional submanifold is completely free from the result on conformal metrics actually. Okay, so suppose that we have an isometric embedding of a compact Riemannian manifold with boundary into Euclidean space of dimension at least 3 and codimension at least 1. Then we can find a sequence of embeddings which coincide with the original one in a neighborhood boundary, converge to the original one uniformly, and the first eigenvalue of the corresponding submanifold is arbitrarily large. Okay, so in this setting, we know that there exist conformal Riemannian metrics where we can actually choose the conformal factor to be 1 in a neighborhood of the boundary and strictly greater than 1 in the rest of the manifold, so that the first Steklov eigenvalue goes to infinity. Okay, so now we consider M and not with such a conformal metric, and then the original embedding is isometric in a neighborhood of the boundary and strictly short in the rest of the manifold. Therefore, from the previous corollary, we obtain our theorem. Okay, so this is basically how our method works. And for surfaces, the situation is quite more interesting because, as we said, in the case of surfaces, one should also change the topology of the surfaces, so we cannot apply the C1 embedding theorem in such a straightforward way. Since we have some time left, let's have a look at the sketch of the proof, at least. So our theorem is the following. Suppose that we have a compact surface with boundary in a Euclidean space of dimension at then in any tubular neighborhood of our surface, there is a sequence of compact surfaces with the same boundary and arbitrarily large first non-zero Steklov value. So let's discuss the proof in the case where sigma, our surface is orientable with connected boundary. Again, we'll exploit the construction that is already known outside the Euclidean space. So it is known that there exists a sequence of orientable surfaces with connected boundary and arbitrarily large first normalized Steklov eigenvalue. So we can rescale the Riemannian metrics of the surfaces and suppose that the length of the boundary of sigma n is equal to the length of the boundary of the surface that we have inside the Euclidean space. Okay, now since the first eigenvalue of sigma n goes to infinity, we know that the genus of sigma n also goes to infinity. Therefore, after passing to a subsequence if necessary, the genus of sigma n is greater than the genus of the surface that we have inside the Euclidean space. Okay, so let's suppose that the difference genus of sigma n minus the genus of sigma is some natural number kn. Now for each n, we remove kn open disks from our surface in the Euclidean space and glue sufficiently small tori. And in this way, we obtain a surface Sn containing the tubular neighborhood we want to work with the same boundary as the original surface. And then for each natural number n, we have that sigma n and Sn are both orientable with one boundary component and the same genus. Therefore, from the topological classification of surfaces, they are diffeomorphic. Okay, so we have a diffeomorphism from sigma n to Sn, the surface in the Euclidean space, which, strictly speaking, we can compose with the inclusion of sigma n in the Euclidean space and get a smooth embedding from the surface Sn into the Euclidean space with image the surface Sn. Of course, this is very nice topologically, it's a smooth embedding. However, geometrically, it does not have any nice properties yet. We know, however, that Fn preserves the length of the boundary. And it turns out that we can do, in this case, a reparametrization, so to speak. So we can compose Fn with a diffeomorphism sigma n. And then the differential of the composition is actually an isometry on tangent planes at points on the boundary. Okay, this is something related to the diffeomorphism group of an annulus or a cylinder, actually, and which is something that we can always do as long as the initial diffeomorphism preserves the length of the boundary. Okay, so without loss of generality, we suppose that Fn has this property. And this means that the Riemannian metric of sigma n and the induced Riemannian metric from the Euclidean space, the Fn, actually coincide on the boundary. So there is a neighborhood of the boundary where these two metrics are not that different in the sense that they're quasi-isometric with some fixed ratio. Now we change the Riemannian metric of our surface as follows. In a smaller neighborhood, we keep the Riemannian metric induced from the Euclidean space. Inside the neighborhood that we have control, we change from one metric to the other. And then outside this neighborhood, we keep the original Riemannian metric of our surface. And by doing this, we obtain a Riemannian metric, which is quasi-isometric to the original metric with the same fixed ratio. So first Steklov eigenvalues are in particular with respect to these metrics, they're also unbounded. So from now on, we think of our surfaces on these metrics. And it's very important for us that with respect to these metrics, the embedding Fn is actually isometric in a neighborhood of the boundary. So we're very close to applying our corollary. However, it's not really strictly short elsewhere. However, that is very easily fixable. We can just change the Riemannian metric conformally. A conformal factor that is 1 in a smaller neighborhood of the boundary and then becomes arbitrarily large, so that the embedding is strictly short elsewhere. And by doing this on a surface, the Steklov spectrum does not change at all. And finally, we can apply the same corollary and complete the proof for construction. So that's everything we had to discuss. Thank you very much for your time and your attention.
Okay, thank you. Thank you very much for your talk. So let's open the floor for questions. So if you have any question or comments, you can unmute yourself or put it in the chat. So maybe I have a question. So here you are constructing like manifold either by a word product or in this case kind of submanifold of Euclidean such as sigma 1 goes to infinity. Do you think your method or your technique helped to create like a large a spectral gap between like sigma 1 and sigma 2, so like
I've never really thought about it. I guess these constructions could be helpful even for such constructions, but I don't really see a way, a very straightforward way in order to
Okay.
modify them.
Okay, so you mainly use the fact that the Rayleigh quotient is the minimum, so it's not like this explicit calculation of the word product things that you do the compare.
Okay, so we have an expression for the Steklov spectrum of the word product. So about here. Yep, so one question I guess would be then for the diffusion operator itself, let alone the plus type operator symbol, if we can make, say, sigma 1 small and sigma 2 large. Yes, that's a more fundamental problem that needs to be tackled, I guess. Also, in the case of conformal Riemannian metrics, I'm not sure if there has been such a construction yet.
Okay, thank you. Is there any other question or? So if not, let's thank Panagiotis again for his talk. Thank you.
Thank you very much.
Yeah, and we reconvene next week with the talk of David Tedros. He will talk about critical metrics of eigenvalue functionals via subdifferentials. So see you next Monday. Thank you.
Bye.